Have you ever just looked at the world and wondered, how do we make any sense of it? You know, all the chaos? Well, it turns out it all starts with a couple of incredibly simple ideas. They're like a secret language for logic and order. And today, we are going to decode them. Let's jump right in.
So that's the big question, right? And the answer isn't some crazy complicated formula. Nope, it actually starts with something you do every single day without even thinking about it. Just putting things that belong together into groups.
I want you to think of it like this. We're about to build a giant skyscraper of logical reasoning. And, just like any skyscraper, it has to start with one single, absolutely essential piece, a building block.
And our very first building block, the fundamental brick for everything we're about to construct, is an idea called a set.
A set is, well, it's just a collection of stuff. That's it. Think of your grocery list. That's a set. The players on your favorite sports team. That's a set. Now, there are two key rules here. No item gets repeated, and the order does not matter. Your grocery list is the exact same list whether you write down apples, bananas, carrots, or carrots, apples, bananas.
So, once we have these collections, these containers of information, we can start doing some pretty interesting things with them. And the two most basic things we can do are either combine them or find out what they have in common.
And this is where it gets really powerful, because it all comes down to two tiny little words, or and. A union is everything that's in set A or in set B. You just throw it all together. But an intersection is only what's in set A and in set B. It's just the overlap. That tiny difference in language makes a huge difference in the outcome.
Okay, so we've got our collections. The next question is obvious, right? How do we build reliable connections between them? Well, that's where our next building block comes into play, the function.
A function is really just a rule. It's a process that connects an input to a single predictable output. My favorite example? A coffee machine. You put in a coffee pod, that's your input from the starting set, and you always get out 1 cup of coffee, your output in the ending set. It's a totally reliable, one-way street.
Let's just walk through it real quick. 1. You start with an input. Let's say you press the number 5 on an elevator keypad. 2. You apply the rule, which is the elevator's programming that connects that button to a specific floor. 3. You end at a single output. The elevator doors open on the 5th floor, every single time. That predictability is what makes a function so incredibly powerful.
But here's the thing. Not all functions are created equal. Some connections are just different. By looking closely at how they connect the inputs and outputs, we can discover some pretty special properties that unlock even more powerful ways of thinking. So let's take a look. So, the first question we can ask is the connection one-to-one? When it is, we call that function injective. This means every output, every destination, is linked to at most one starting point. Think of it like a classroom where every student has their own unique ID number. That's injective. But what if 2 different students had the same ID number? Well, that would be chaos, and it would be non-injective. Okay, next question. Does the function actually cover all the bases? A function is surjective if it can hit every single possible output in the ending set. Think of a vending machine. If it's got a button for every single snack inside, it's surjective. But if there's a lonely bag of chips in there with no button to select it, that machine is non-surjective.
Now, what happens when a function is both injective and surjective? Well, that's when we hit the jackpot. We call this a bijection, and it is the absolute gold standard of connections. It's a perfect one-to-one match. Every input has one unique output, and every output is connected to one unique input. No loose ends, no ambiguity, just a perfect pairing.
So, why do we care? Why does this even matter? Because once we understand these perfect pairings, a whole new world opens up. We can use this logical structure to tackle something incredibly practical, the art of counting really complex possibilities. You might have heard of it as combinatorics.
Let's make this totally real. Imagine there's a race with 8 runners. We want to know how many different ways the gold, silver, and bronze medals can be handed out. This isn't just a simple count, it's a very specific kind of mapping problem that we can now solve.
This exact problem is what mathematicians call an arrangement. And here's the really cool part. An arrangement is just a real-world example of an injective function. We are creating a one-to-one mapping from the podium spots to the runners. And it has to be injective, right? Because you can't have the same runner win both first and second place. So, what's the answer?
How many possible arrangements are there? Well, for the first place spot, we've got 8 runners to choose from. Once that's decided, we've only got 7 runners left for second place, and then 6 left for third. So you multiply 8 times 7 times 6, and you get 336 possible podium finishes. And we figured that out just by understanding the hidden structure of the problem.
Now, it is absolutely crucial to see that in an arrangement, the order is everything. Gold, silver, bronze is totally different from bronze, silver, gold. This is not the same as a combination, like, say, forming a committee of 3 people. For a committee, who cares who was picked first, second, or third? The final group is all that matters.
This brings us to a really deep, kind of mind-blowing idea. What does it actually mean for 2 groups of things to have the same number of items? The true mathematical answer is that you can create a perfect one-to-one pairing, a bijection, between them. This concept is so powerful, it's what lets mathematicians compare the sizes of infinite sets, but that is a whole other explainer for another day.
So, what's the big takeaway here? Sets and functions are not just things you learn in math class. They are a universal language for building systems, for understanding rules, for describing relationships. From the code that runs your phone to the databases that organize the world's information, these simple building blocks are, quite literally, the foundation of structured thought.
So I'll leave you with this. Think about your own day. What relationships could be described by functions? The relationship between your fingerprint and unlocking your phone, that's a function. The way a search engine takes your question and matches it to a set of results, that's built on sets and functions. Once you start looking for it, you'll see this invisible architecture everywhere, bringing order to our very complex world.